Electrical engineering is not just one subject. It consists of many different subfields or concentrations. So two people who graduate in electrical engineering might go into two totally different career paths in their own subfield of expertise. The most common subfields you'll hear are power, electronics, which are probably the two most common, then RF or radio frequency, also called telecommunications, and controls. There are other ones that I'll talk about later, but let's dive into what these subfields are, the careers you can get into, elective classes you might take, and senior projects that have been done. Power engineering focuses on the generation, transmission, and distribution of electric power. These engineers could work at an electric power plant when it comes to generating and distributing large amounts of electric power. They could work on solar energy or wind energy. Or they could work on the power electronics and battery of electric vehicles. So if you want to make electric cars run further on one charge, then power might be a great concentration for you. So one of the electives you could take is power electronics. This is where you learn about control and conversion of electric power through electronics. For example, an AC to DC converter is a very popular power electronics device. Our wall outlets, at least in most countries, have an alternating voltage, which in turn creates an alternating current, or AC. If you want to charge your laptop, you need a constant voltage, like maybe 15 volts, which causes a direct current, or DC. So how do we go from that changing voltage to a constant one, or AC to DC? Well, inside all of our chargers, there's an AC to DC converter, which are circuits that change the changing voltage into a constant one to charge our devices. You'll learn various circuits that can do this. Don't worry about not understanding what this is right now, just realize you will use circuit analysis techniques and electronics knowledge to then analyze these circuits that have a specific use. You'd also learn DC to DC converters, which are circuits that change one constant voltage to another. They are normally seen in mobile devices to maintain a constant voltage regardless of what our battery level is at. Then, as you can guess, there's AC to AC and DC to AC as well. These can be used in light dimming and emergency lighting systems respectively. Now these can all be used for so many more applications, but all these were the simple ones we can all understand. Power electronics can be seen in audio amplifiers, battery chargers, wind turbines, motors, and so on. There's of course way more to a power electronics class, but it's just too complicated for a video like this. Then you could also take an electric energy conversion class, which is essentially learning specifically about solar energy, wind energy, grid connected systems, and so on. And there are other classes, but I'm going to move on to senior projects. But remember, every school will differ in the electives that they offer, but this is the overall idea behind the power concentration. Senior projects that students did in the power subfield include an energy harvesting bike that could convert mechanical energy into electrical energy, a solar panel tracker where the lenses could track the sun throughout the day so maximum energy could be converted, and a cell phone charger powered by wind energy via a small wind turbine. So hopefully you have a good idea of what the power concentration is. Now let's move on to electronics. This is about using electrical components to design various devices. These people design and improve our electronics, including computers, phones, radios, TVs, robotics, audio players, medical devices, and so on. This is probably what most people think of when they imagine an electrical engineer. But realize it's easy to look at these devices that use electronics and become interested, but you have to work with the electronics that make it work. You need to make the amplifier circuits, the filters, the oscillators, the logic circuits, etc. So an example of an elective class you might take is filter design, which I want to go into a little detail on. As I said in the computer engineering video, when something is receiving many different signals, like a radio antenna that's receiving many different radio stations at once, how do we remove the unwanted ones? Well, we have a filter circuit that blocks out or filters certain frequencies, but allows other ones to pass through. A simple filter circuit could look like this. Even if you don't know circuits yet, you can still see how simple these can be with just a resistor and capacitor. This removes higher frequencies from a signal, but the consequence of being simple is that it's not very good. It doesn't cut off frequencies very sharply. There are many different radio stations, for example, and let's say we want to listen to 97.3 FM. We want a sharp filter that completely cuts off other stations and just passes the station we're at. If it weren't sharp enough and you were listening to that radio station, you might be able to faintly hear sounds from the other stations because they weren't being totally filtered out, and that would be pretty annoying. So larger circuits are needed which allow for better and sharper filters. It's actually impossible to make a perfect square filter like above, but with more components you can make a very sharp filter that mostly blocks out frequencies or radio stations that you don't want. And this right here is the basics of what a class like this would be like. What values do those circuit components have to be? What frequency would be the center one they are allowing to pass, like 97.3 FM from above? How would changing the values on the left change that center frequency? And how wide would this graph be, or what is the range of frequencies it will allow to pass? If it's too wide, it might let in other stations or frequencies that we don't want to pass through. You can also take an advanced analog circuits class or an op-amp design class, where you learn about other types of circuits like you did filters. But these are kind of tough to explain, like oscillators, phase lock loops, analog to digital converters, and so on. So don't worry about what those are for now. If at the very least you enjoy basic circuits, then you may really enjoy this subfield, because it's just using circuit analysis techniques to create circuits that have a specific purpose. So senior projects that people in electronics did include an analog audio amplifier, which would be used for a speaker, a car alarm system, a heart rate monitoring control system, or an audio distortion circuit that would enhance the quality of sound from an electric guitar by adding certain frequencies into the signal. Now moving on to RF or telecommunications, which is all about wireless communications and high frequency systems. These engineers could work on satellite communications, radar systems, and high frequency electronics for those radar systems all the way to quantum computers. Now this is one of the most math-intensive paths you can go as any type of engineer. So before considering this, make sure you really enjoy calculus level math, vectors, and physics, specifically with electromagnetic waves. Even if you have just taken basic physics in high school, make sure you at least enjoyed the electricity and magnetism portion. So an elective class you could take is digital communications, in which you learn how to take a digital signal and encode it into a wave to be sent off wirelessly. I've shown this animation before in which a voltage signal is encoded into an AM or FM signal. Well, you use that same technique but for a digital signal with ones and zeros, which as you may know from other videos is just a high and low voltage. We can't just transmit that as it is, so we take an alternating voltage and change its frequency for the ones and the zeros. You could also learn how to defend against someone trying to jam your signal by frequency hopping or jumping between frequencies that only your system knows. You could take an antennas course in which you learn about how antennas send signals and different types of antennas. This is a lot of physics and electromagnetic waves, like determining how current in a wire creates an electric and magnetic field at some distance away. Or you might learn how to predict how far a signal will travel based on the antenna parameters. You could take a high frequency circuits class, which could be considered RF or electronics. But let me explain real quick why high frequency is more difficult and different than low frequency. If you attach a rope at a fixed end and started shaking it up and down very quickly, waves would start to travel down the rope. But then reflection would occur once they reach the end, and then those reflections would combine with the incoming waves, and it would get quite complicated mathematically. Well, when you have a very fast changing voltage or high frequency signal, like radio signals, TV signals, and so on, that you put into a circuit, the same thing happens. Current and voltage will travel down the wires, but will reflect back and cause complicated current and voltage equations within your circuit. Way too complicated to explain here, but that's the idea. So if you want to build an amplifier or a filter, it's not exactly the same as before because you have to account for those reflections. And this is another reason this concentration is so math heavy. Senior projects done in RF have included an RFID home lock, so you could open a door with just an RFID card reader instead of a traditional key, a remote controlled dish antenna, an alternative antenna to traditional Wi-Fi antennas for better wireless internet connection, a signal jammer that interrupts a signal from a remote controlled car, and a wirelessly controlled robotic vehicle. And the last main subfield is controls. You really only learn the very basics of this in your required classes, and it is pretty math intensive. Control systems typically use sensors that monitor some output, then those measurements are fed back to something else which makes corrections. For example, your car's cruise control continuously monitors your speed and adjusts accordingly if it changes. Without that feedback of your speed, if your car started going up a hill, the speed would not adjust. Controls can be seen in automatic driving, aircraft flight control, guidance and navigation for cars, ships, aircrafts, and spacecrafts, or temperature control and thermal regulation. Just think simply to air conditioning in the house that measures the temperature and turns the AC on or off accordingly. It's all control systems. The classes are more confusing, so I'm not going to go over those. Just know it is math intensive, but not quite as much as RF. Senior projects and controls include an airport runway heating system that would detect snow and ice buildup to ensure safety of incoming flights, or a seizure detection system, or an electric vehicle steering control system. Now, like I said, there are other subfields that I want to explain briefly as their own category. One being computer. You can specialize on the computer sides of things as an electrical engineer and take some of their elective courses, which I've discussed in other videos. Projects these students have done include a GameCube to N64 controller converter, a surge protector controlled by an Android phone that could turn off the surge protector and monitor electric usage to minimize energy consumption, and a lighting system that is controlled and monitored over Wi-Fi in which mobile devices could control the application. Optics is another subfield. This may be grouped with telecommunications, but I put it separately because it's kind of unique. It's mainly about using light to transfer data. Fiber optic cables use light to transfer data in computer networking as an example, or they can be used in sensors when it comes to sensing something like temperature or pressure. Projects included converting an electric signal to a light signal, then transmitting it through air over a short distance to a receiver, or an underwater audio transceiver in which visible light communications are used to transmit and receive the sound. And lastly, one more that I want to throw in is digital signal processing. This involves using computers to perform signal processing operations. So instead of having a voltage signal and putting it through a circuit to, let's say, filter the signal like you would in electronics, you have a sampled signal, kind of like taking pictures at various points, and you put it through a computer or digital signal processor to do the filtering, amplifying, and so on with those signals. One project was to create a noise cancelling device, so if someone is speaking into a microphone and there's unwanted noise in the background or whatever, the device could remove that noise. Filtering on a computer has much more power than filtering with just one circuit. And by the way, this is a math-intensive subfield too, because those filtering techniques are all math manipulation. And I'm going to end there because I've thrown a lot at you. So to summarize, various types of people with different interests may go into electrical engineering. You will have the same classes in the beginning where you learn the basics of all the main subfields I've talked about. But then students will find interest in different fields that they'll dive into. By their third or fourth year, students will be taking different elective classes from one another. And they'll also be working on totally different senior projects in their own areas of interest. If any of these interest you, then electrical engineering might be a great major for you. And you don't have to like them all. Many students in power, let's say, really hate RF. So don't worry if you don't like all the subfields.